What if I told you that one of the most critical steps in welding a pressure vessel, pipeline, or power plant component happens after the welding arc goes out? Welcome to post-weld heat treatment, PWHT, the heat treatment process that can mean the difference between a safe, long-life weld and a catastrophic failure. I'm Welding Fabrication World, and in today's video, we're going deep into PWHT, what it is, why it's mandatory in so many welding codes, how it actually works at the metallurgical level, and exactly how it's performed in industry. Whether you're a welding engineer, an inspector, a QA, QC professional, or a student studying welding metallurgy, this is the video for you. Let's get started. Post-weld heat treatment, or PWHT, is a controlled thermal process applied to a welded joint and its surrounding base material after welding is completed. The weld is subjected to a carefully regulated heating cycle, raised to a specific temperature, held there for a prescribed period called the soak or hold time, and then cooled at a controlled rate back to ambient temperature. PWHT is not simply letting a weld cool on its own. It is a precision metallurgical operation governed by international welding codes and material standards. Why do we perform PWHT? There are four primary metallurgical and mechanical objectives. First, residual stress relief. During welding, extremely high localized heat causes the metal to expand and contract unevenly. The surrounding cold metal restrains this movement, trapping large internal stresses in and around the weld. These residual stresses, which can be as high as the yield strength of the material, act as an additional static load on the structure and significantly increase the risk of brittle fracture, stress corrosion cracking, and fatigue failure. PWHT relieves these stresses by allowing the metal to creep and redistribute at elevated temperature. Second, hydrogen diffusion. During welding, especially with coated electrodes or in humid conditions, atomic hydrogen can diffuse into the heat-affected zone. This hydrogen causes hydrogen-induced cracking, also known as cold cracking or delayed cracking, which can occur hours or even days after welding. PWHT drives this hydrogen out of the microstructure by raising the diffusion rate. Third, tempering of hard microstructures. The rapid heating and cooling of welding creates hard, brittle microstructures, particularly martensite, in the heat-affected zone of hardenable steels. PWHT tempers these hard phases, improving toughness and ductility. Fourth, dimensional stability. For high-precision machined components, PWHT reduces distortion risk by relaxing locked-in stresses before final machining. To truly understand PWHT, we need to understand what welding does to the microstructure of steel. When an arc weld is deposited, the area immediately adjacent to the fusion line, called the heat-affected zone, or HAZ, experiences a dramatic thermal cycle. The peak temperature at the fusion boundary approaches or exceeds 1400 degrees Celsius. As we move away from the weld, peak temperatures decrease across the HAZ. This creates distinct microstructural zones within the HAZ itself. A coarse-grained HAZ close to the fusion line, a fine-grained HAZ, and a partially transformed zone further out. In carbon and low-alloy steels, if the cooling rate after welding is fast enough, which it almost always is in thick sections or restrained joints, the austenite formed in the HAZ transforms to martensite. Martensite is an extremely hard, body-centered tetragonal phase. Its hardness increases with carbon content. While high hardness sounds beneficial, in the HAZ context martensite is a problem. It is brittle, it is susceptible to hydrogen cracking, and it contains very high residual stresses from the transformation itself. The critical parameter we use to predict martensite formation is the carbon equivalent, or CE. Common formulae include the IIW formula and the PCM formula used for high-strength steels. When carbon equivalent exceeds approximately 0.40, and particularly above 0.45, PWHT or at minimum preheat becomes essential. During PWHT, as the temperature rises toward the stress relief range, typically 550 to 720 degrees Celsius for carbon and low-alloy steels, the yield strength of the steel drops significantly. At these elevated temperatures, plastic deformation and creep allow the highly stressed regions of the weld and has to yield locally and redistribute the residual stress. The result, after controlled cooling, is a component with dramatically reduced residual stresses, typically by 70 to 90% for a proper PWHT cycle. Key international standards governing PWHT. PWHT requirements are not optional recommendations, they are mandatory requirements specified in internationally recognized welding and pressure equipment standards. The three most important standards families are ASME Boiler and Pressure Vessel Code, specifically Section 8 Division 1 and Section I for power boilers, and Section X for welding procedure qualification. ASME 1.1 Structural Welding Code, Steel, which covers structural applications. And the N 13445 series for European unfired pressure vessels, alongside N ISO 15614 for welding procedure specification and qualification. Each standard specifies mandatory PWHT based on material type, material thickness, and preheat history. Under ASME Section 8 Division 1, PWHT is mandatory for P91 group materials, essentially carbon steels, when the nominal thickness at the joint exceeds 32 mm, or approximately 1.25 inches. For alloy steels such as 1.25 cr 0.5 mo, the threshold is considerably lower, often 16 mm, and for 2.25 crossing 1 mo materials like P91 5A Group 1, PWHT is mandatory regardless of thickness. Importantly, preheat can be used to avoid PWHT in some cases for P91 materials below the thickness threshold, but this must be qualified in the welding procedure specification. Let's walk through the key P-number material groups and their PWHT requirements under ASME Section 8 Division 1. Starting with P-1, your standard carbon steels, grades like SAW 516 grade 70 and SAW 106 grade B. PWHT is required when the joint thickness exceeds 32 mm, or 1 1/4 inches. Below that threshold, preheat can be used as an alternative under qualifying conditions. Moving to P-3, half molybdenum alloy steels such as SAW 204 grade B. The mandatory thickness threshold drops to 16 mm, or 5/8 of an inch. P-4 covers the 1 1/4 chromium, half molybdenum steels, SAW 387 grade 11 being the classic example. Again, the threshold is 16 mm, reflecting the increased hardenability of this alloy group. Now things get more serious. P-5A, the 2 1/4 chromium, 1 molybdenum steels, SAW 387 grade 22, PWHT is mandatory at any thickness. There is no exemption based on thickness alone. The same applies to P-5B, 5 chromium, half molybdenum steels like SAW 387 grade 5. PWHT is mandatory regardless of how thin the section is. And finally, P-15E, the 9 chromium, 1 molybdenum vanadium steels, grade P91. Not only is PWHT mandatory at any thickness, but this material carries special requirements that go beyond standard code tables, including a tightly controlled soak temperature window that we'll cover in Section 7. Any PWHT procedure is defined by 4 critical parameters that must be controlled, monitored, and documented. First, heating rate, the rate at which temperature is increased from ambient to the soak temperature. For most carbon and low alloy steels, codes limit heating rates to prevent excessive thermal gradients across thick sections. A common limit is 55 to 220 degrees Celsius per hour, with the specific value often determined by dividing a constant by the material thickness in inches. Second, soak temperature, the target temperature at which the component is held. For carbon steels, this is typically in the range of 595 to 650 degrees Celsius. For crossing Mo alloy steels, higher temperatures are required. P91 steels, for example, require 730 to 775 degrees Celsius. Third, hold or soak time, the duration at soak temperature. ASME 8 typically requires a minimum of 1 hour per inch of thickness, or a minimum of 15 minutes for thickness less than 1 inch. Extended hold times may be required for thick-walled components or for special applications. Fourth, cooling rate, the rate at which the component is cooled from soak temperature back to ambient. Typically, a maximum cooling rate of 260 degrees Celsius per hour applies above 315 degrees Celsius. Below this temperature, free air cooling is generally permitted. Slow cooling rates are particularly important for thick sections to prevent thermal shock and reintroduction of residual stress. Accurate temperature measurement is absolutely critical to PWHT. The wrong temperature, too low and residual stress relief is inadequate. Too high and you risk over-tempering, grain growth, or even exceeding the lower critical temperature AC1, which would re-austenitize the material and undo the entire treatment. Thermocouples are the primary temperature measurement devices. Type K thermocouples, chromal alamel, are commonly used for temperatures up to 1260 degrees Celsius. For P91 and other high-alloy steels requiring precise PWHT in the 730 to 775 degree window, Type N thermocouples may be preferred for better accuracy at elevated temperatures. Thermocouples must be attached directly to the component, by welding, mechanical fastening, or high-temperature cement, not to the heating element or insulation blanket. Code requirements specify minimum numbers of thermocouples based on the heated length of the component. PWHT can be performed using several heating methods, and the selection depends on component geometry, material, location, and access. Electric resistance heating, using flexible ceramic pad heaters or resistance wire, is the most common method for field PWHT of pipelines and pressure vessels. It provides excellent controllability. Induction heating uses electromagnetic induction to heat the component directly. It is faster and produces excellent temperature uniformity for pipe-to-pipe girth welds. Furnace PWHT, where the entire component is placed in a gas-fired or electric furnace, is the preferred method for shop fabrication of pressure vessels and heat exchangers, as it provides the most uniform temperature distribution. Flame heating using gas torches is the least controlled method and is generally limited to small components or pre-qualified applications. PWHT procedure, inspection and documentation. Just like welding itself, PWHT must be performed to a written procedure. The post-weld heat treatment procedure, sometimes abbreviated PWHTP, is a qualified document that defines all the critical parameters: the heating method, thermocouple type and number, heating rate range, soak temperature range, hold time, cooling rate limit, temperature differential limits across the heated zone, and the documentation requirements. For ASME codework, the PWHTP must be referenced in or consistent with the qualified welding procedure specification. Changes to essential PWHT variables may require re-qualification. For local PWHT of girth welds in pipelines and piping systems, it is critical to heat not just the weld itself but an adequate width on either side. ASME B31.3 process piping, for example, requires that the heated band extend at least 1 inch beyond the edge of the weld on each side, and for circumferential welds, the entire circumference must be heated uniformly. The temperature differential across the heated zone must typically remain within 65 degrees Celsius. Failure to maintain adequate heated band width results in a steep temperature gradient, essentially a new stress concentration, which can actually worsen conditions in the unheated HAZ. FTER-PWHT, hardness testing is the primary method used to verify that the treatment has been effective. The HAZ, which contained the hardest microstructure, is the critical measurement location. For carbon and low-alloy steels, maximum permissible hardness after PWHT is typically 248 HV10 per ISO 156141, or 22 HRC, which corresponds broadly to a microstructure that has been adequately tempered. For P91 steels, hardness requirements are expressed as a range, typically 190 to 265 HV, because hardness that is too low indicates over-tempering and degraded creep strength. Vickers hardness testing is preferred over Rockwell for weld surveys because the smaller Vickers indentation allows more precise mapping across the narrow has. Documentation of PWHT is mandatory for all coded work. At minimum, the PWHT record must include the identification of the component and weld joint reference numbers, the PWHT procedure number and revision, date and location of PWHT, operator identification, thermocouple identification and calibration records, the time temperature chart recorder trace or equivalent electronic data record, and a signed certification of compliance by the responsible inspector or Level 3 NDE coordinator. This documentation forms part of the data report package submitted to the authorized inspector and ultimately to the end user or regulatory authority. Special topics: P91 steel, dissimilar welds and PWHT exemptions. P91 steel, 9% chromium, 1% molybdenum with vanadium, niobium, and nitrogen additions, is used extensively in ultra-supercritical power generation for steam headers, main steam piping, and turbine components operating at temperatures up to 600 degrees Celsius and pressures above 20 megapascals. PWHT of P91 is mandatory regardless of thickness and is one of the most demanding PWHT operations in industry. The challenge is that P91 requires a very specific tempering temperature window, 730 to 775 degrees Celsius. Below 730, tempering is inadequate and creep strength is unacceptably low. Above 775, there is a risk of reaustenitization, which resets the microstructure and destroys the carefully controlled tempered martensitic structure that gives P91 its creep strength. Additionally, P91 must be cooled below the martensite finish temperature, approximately 100 degrees Celsius, before PWHT begins, to ensure complete martensite transformation. Preheating to 200 to 300 degrees Celsius for welding and careful interpass temperature control, maximum 300 degrees Celsius, combined with no cool PWHT procedures requires very careful thermal management. Hardness testing after PWHT is mandatory and must fall within the 190 to 265 HV window to confirm an acceptable tempered martensitic microstructure with adequate creep strength. Dissimilar metal welds, for example, joining carbon steel to austenitic stainless steel, or low alloy steel to Inconel buttered nozzles, present unique challenges for PWHT. Standard PWHT temperatures for carbon and low alloy steels, around 620 degrees Celsius, can be detrimental to austenitic stainless steel weld metals, potentially causing sensitization, carbide precipitation, and sigma phase formation. In these cases, engineering solutions include the use of nickel alloy butter layers on the alloy steel side, which allows PWHT to be performed before the austenitic or nickel alloy fill passes are deposited. Alternatively, a lower PWHT temperature may be acceptable for the low alloy steel under certain code cases, or the design may specify weld procedure qualification testing that demonstrates acceptable properties without PWHT on the stainless side. Not every weld requires PWHT, and codes provide specific exemption criteria. For P91 carbon steels below the mandatory thickness threshold, PWHT may be omitted provided adequate preheat was applied during welding, the welding procedure was qualified without PWHT, and the service conditions do not involve hydrogen service, corrosion fatigue, or other aggressive environments. ASD 1.1 provides its own exemptions based on preheat and heat input requirements. The use of low hydrogen electrodes, classified as EXX18, EXX16, or better, stored and dried to manufacturer's requirements, is a key alternative measure that reduces hydrogen-induced cracking risk and supports PWHT exemption justification. Always document the exemption basis with engineering authority approval. Let's bring everything together. Post-weld heat treatment is a mandatory, precision thermal process, not an afterthought. It achieves 4 critical objectives: residual stress relief, hydrogen diffusion, tempering of hard-has microstructures, and dimensional stabilization. It is governed by internationally recognized codes including ASME, AWS, and the N standards, with mandatory requirements driven by material type and thickness. The 4 PWHT parameters, heating rate, soak temperature, hold time, and cooling rate, must all be controlled, monitored, and documented. The choice of heating method, thermocouple placement, heated band width, and post-treatment hardness verification are all critical quality gates. And for high alloy materials like P91, PWHT becomes an even more exacting science with a precise temperature window that directly governs the long-term creep life of the component. Number 1. PWHT is a code requirement. Always check the applicable standard and your approved WPS. Number 2. Know your material P number and thickness. These drive the mandatory PWHT threshold. Number 3. Control all 4 parameters, heating rate, soak temperature, hold time, and cooling rate, and document everything. Number 4. Thermocouple placement is critical. Attach directly to the component, never to insulation or heating elements. Number 5. Maintain adequate heated bandwidth to avoid creating new stress concentrations. Number 6. Post-PWHT hardness testing is your verification that the treatment worked. And number 7. For P91 and other critical alloy steels, treat PWHT as a precision manufacturing operation. The soak temperature window is non-negotiable. If you found this video valuable, please like and subscribe. It really helps other professionals in welding, inspection, and QA find this content. Drop your questions in the comments below. I read every one. Coming up next in this series, we'll be covering weld procedure specification development under ASME Section X, and non-destructive examination methods for pressure welds. Links are in the description. Until next time, stay qualified, stay compliant, and keep welding to standard.